Hello. Today I'm going to talk to you about this concept of an amplifier with the gain of 1 or unity gain amplifier. Sometimes this amplifier is called a buffer. Now, let's just start with looking at the circuit and quickly analyze it. That would be our first attempt. This is the circuit. That's all there is. So it would be a really simple analysis. You're going to apply an input here, and you're going to get an output right there. Really, there's not much to do, quite honestly. There are only 2 nodes in this circuit. This is, if we follow our normal routine of identifying nodes and everything, this is one node, and this is the other node. Now, the interesting thing here is that obviously we know that for ideal amplifier, this current is equal to 0. So there is no current in the circuit. And the other equation for the component would be, because we have a negative feedback, would be the fact that these 2 terminals are actually equal to each other. So if or follow each other. So if I write that equation, I think you can quickly see that VI being equal to V out gives you a gain of V out divided by VI being equal to 1. That's why this circuit is called a unity gain amplifier or a buffer. Okay, so with that quick introduction to this concept, the question becomes, why would anyone care about an amplifier that only gives you a gain of 1? In other words, it's as if saying that this output is the same as the input in a way, right? Or at least at the first glance, that's what it looks to be. But you are wrong if you think that way. So let's look at this. Let's use actual inputs and outputs. So what do I mean by that? If you take this input and connect it to any other system that gives you a signal, and looking back to that system or black box, you can obviously turn it into a Thevenin model, right? So let's do that and connect this to a Thevenin equivalent or whatever you're connecting to this amplifier, which would be a voltage in series with a resistor. And then you're going to feed this to any kind of load. So I'm going to call that RL. So you're taking an input and then you're amplifying it. If you're not really amplifying it, but you're just basically feeding the same signal to a load. So let's do the calculation again here. If you notice, actually nothing changes here. Even though that I added these components, still this current is 0. So this voltage right here, which is Vs, is going to end up being the same voltage as this one because there is no current passing through the resistor. And therefore that voltage, which still is my output, is the same as my signal. So V out ends up being same as Vs in this new circuit. So V out over Vs is still 1. The only difference is that this time there is actually current in the circuit. Because we connected this to a load, now there is a current, and that let's call that IRL. I load, it's okay. So let's just call it IL. And that current IL is equal to V out divided by RL, which is the same as Vs divided by RL. And that current obviously is not coming from this. It is actually supplied by the op amp itself. And that's where the beauty of this circuit is. Before I get to that, so this is also let's assume that we don't know what the functionality of a unity gain op amp is and just remove it because these 2 voltages seem to be the same and see what happens. So if I remove that and I have the same source, no amplifier, and then connect it to RL, this is a very simple circuit that you can easily analyze, right? V out is a voltage divider over Vs. So V out is equal to RL over RS plus RL Vs. You can clearly see that if you remove that buffer, even though that it looks like that it's not doing anything, it actually changes what you're going to end up getting, which means that V out over Vs in this case is not 1. It's a ratio, which is smaller than 1, obviously. Okay, so what happened? What happened is that in this situation, the current that was fed to the load was coming from the op amp, and that current actually was not being supplied by the source itself, and instead was being supplied by the voltages, power supply voltages that we didn't show in the op amp. And because of that, you didn't lose any voltage in this case. So the same voltage that was supplied by the signal source was directly applied to your load. But if you remove that, obviously that wouldn't be the case, because there is no other source to supply the current. The current has to come from your signal source, and therefore you're going to get a voltage divider. Now the trouble starts to brew when your source is not a very good source, and that happens all the time. What do I mean by that? When a source has a large internal resistance. As soon as you have a large internal resistance and you're trying to feed that to a normal load or even a small load, this ratio becomes extremely small. And at that point, you lose most of your signal by the time that you basically connect the load to your source. And in these situations, this buffer is going to basically play a very important role for you, and that would be to not lose any of your signal because of that large internal resistance of the source or the small value of the load, or combination of the two. Now, let me tell you what those kind of situations are quickly, and then I'm going to conclude. So a lot of times the source of signal that you have could be something that generates a signal passively. What do I mean by that? Meaning that this, for example, could be a transducer, meaning that it takes the energy from one domain and turn it into a voltage or a current in the electrical domain. Any sensor that you might use that directly transforms energy from one domain to the other could actually come to mind. There are a lot of components where you, say, take temperature and turn that into a voltage and current using a certain physical phenomena. And in those cases, the signal that you generate is actually a very small signal by nature. And the internal resistance is not too small. And then if you want to take that and amplify it, if the internal resistance of your amplifier is small, then you get a voltage divider. Whereas if you use a buffer, then you can actually basically maintain the same signal level without losing much. So in other words, even if you're using an amplifier, if the internal resistance of the amplifier, we call it Rn of the amplifier, is not too large, then you end up getting into the same situation where the voltage divider happens and you lose signal. So a lot of times it's a good idea to use a buffer or something that looks like this configuration in order to make sure that you are not losing any of that signal, which means that you want to make sure that the internal resistance of your amplifier is huge. And as a result, or in other words, the current that is going to your amplifier is close to zero. Let me give you a quick example that kind of puts that into perspective, and we're going to conclude with that. So we already discussed that we have two different kind of amplifiers, basic amplifiers that are very typical. One was called the inverting amplifier, where the gain was V out over VI, was basically minus R1 over R2. And then in this case, it was the non-inverting amplifier, where the output over input was 1 plus R1 plus R2. It looks that we can basically use any of these to get any kind of gain, and we generally should be able to use any of these two interchangeably. That's not totally true, because if you notice, this configuration with the non-inverting with the amplifier is very similar to what we had here. In other words, the internal resistance of this op amp becomes the internal resistance of the amplifier, which is ideally close to infinity. And as a result, regardless of what your source internal resistance is, the gain stays the same. Whereas if you use this kind of amplifier, the internal resistance of this amplifier is actually R2. You can quickly calculate that. And therefore, if the internal resistance of your source is large, the total gain of your amplifier is not going to stay the same as that equation. You're going to get a voltage divider, and this would go down. Your gain is going to go down. Therefore, in such situations, using this configuration is preferred over that configuration. Or if you have to, for whatever reason, use a negative gain because you want to change the polarity, what you could do is to actually put one of these amplifiers in front of that. So you end up doing something like this. So this now has the unity gain, and then this part gives you the negative gain. So you overall get the same negative gain that you had before, but this time, if the internal resistance of your source happens to be large, you still don't lose any of that gain, and you keep the same gain for your overall amplifier. And that's the beauty of using a buffer. I hope this has been helpful, and thank you for your attention.